All right, so you've heard the term neural network thrown around everywhere, right? Your phone, self-driving cars, it's everywhere. But what does it actually mean? How does a machine learn to think in a way that feels, well, almost human? Let's get into it. Okay, so take a look at this. It's a number, right? Kind of messy, a little blurry, but your brain probably figured it out in like a split second. No problem. That's the kind of thing we do without even thinking, but it's actually an incredibly complicated task. But here's where it gets really interesting. For you, that was trivial. But if you try to write a regular old computer program to do the same thing, it's a total nightmare. I mean, seriously, how would you even begin to write down all the rules for what a 3 looks like? All the different ways people write them? It's almost impossible. And that exact problem is precisely what neural networks were designed for. As you can probably guess from the name, their whole structure is inspired by the best pattern recognition machine on the planet, our own brains. So the most basic piece of this whole puzzle is something called a neuron. And don't worry, it's not as complicated as the biological thing. For our purposes, just think of a neuron as a little container that holds a number, specifically a number between 0 and 1. We call this its activation. So 0 means it's totally off, and 1 means it's fully lit up. Now, we don't just have one neuron. We have tons of them, and we organize them in layers. The journey starts at the input layer. If our image is, say, 28 by 28 pixels, we'd have 784 neurons, one for each pixel. Then, all the way at the end, we have the output layer. In this case, that's 10 neurons, one for each digit from 0 to 9. And in between, well, that's where we have the hidden layers. This is where all the real magic happens. Okay, so we've got these layers. But what's the big idea? What are we hoping is actually going on inside those mysterious hidden layers that lets the whole thing figure out what digit it's looking at?
Well, the hope is that each layer learns to recognize something more complex, more abstract than the one before it. So, the first layer is just looking at raw pixels, but the next layer might learn to combine those pixels to spot little edges. And the layer after that might combine those edges to find bigger parts like loops and lines. And then finally, the last layer puts those pieces together to recognize the final digit.
You see, the network isn't just memorizing the image of a 9. It's learning the recipe for a 9. It's learning that a 9 has a loop up top and a line on the right. And it learns that an 8 also has a loop up top, but it's paired with another loop down low. It's learning the building blocks. At least, that's the goal. Okay, so that's the big picture, the grand vision. But how does a neuron actually do that? Let's zoom way in, look at just one neuron, and see how it actually thinks and passes information forward. This really is the most important question. How does the pattern of lit-up neurons in one layer determine which neurons get lit up in the next layer? How does a bunch of pixel brightnesses trigger the right edge detector neurons to fire? It all comes down to a couple of really important numbers. The first one is called a weight. Every single connection between a neuron in one layer and a neuron in the next has a weight. Just think of it like a volume knob for that connection. A big positive weight cranks the signal way up, making that connection super influential, and negative weight would do the opposite. A really cool way to think about this is to picture all the weights connected to one neuron as a kind of template or a filter. So if a neuron wants to find, say, a little vertical edge, it might have positive weights, let's call them green, for the pixels where it wants to see an edge, and negative weights, we'll call them red, for all the pixels around it, where it wants things to be dark. So the neuron adds up all these signals, each one multiplied by its weight. But that's not the end of the story. There's one more number called a bias. It's basically a little nudge. After the neuron calculates its weighted sum, it adds this bias. You can think of it as a threshold, like how high does that sum need to be before this neuron starts getting really active? A big positive bias means it's kind of trigger happy and will fire easily. All right, so we've got our weighted sum, and we've added the bias. The result could be anything, right? A big negative number, a huge positive number. But wait, we said a neuron's activation has to be between 0 and 1. So what do? We use something called an activation function. Its whole job is this squishification process. It takes whatever number it's given and squishes it neatly into that 0 to 1 range. So let's just run through that one more time for any given neuron. Step 1, it calculates a weighted sum of all the activations from the layer before it. Step 2, it adds its own special bias. Step 3, it runs that result through the squish function. And boom, that's its new activation. This happens for every single neuron, and their outputs become the inputs for the very next layer.
Okay, so now we know how a single neuron works. Let's zoom all the way back out and just take a second to appreciate the scale of what we're actually building here. Think about it. Every one of those weights and every single bias is a parameter the computer can change. It's like a little knob or a dial that can be turned. And for the simple network we're talking about, the one that just recognizes digits, there are almost 13,000 of those knobs.
And what does all of this add up to? The whole network. It's really just a function. An absurdly, mind-bogglingly complicated function, sure, but a function nonetheless. It takes in 784 numbers, our pixels, and it spits out 10 numbers. The chances that the image is a 0, a 1, a 2, and so on. And this is maybe the most important takeaway. When we talk about a machine learning, it's not some kind of vague, spooky magic. It's this. It's the process of the computer finding just the right setting for all of those thousands and thousands of knobs so that when you feed it a 2, it actually says it's a 2. So we've built the machine, we know what all the parts do, but that leaves us with the biggest, most fascinating question of all. How in the world does the computer know how to tune all 13,000 of those knobs to make them actually work? How does it teach itself to see? Well, that is the process of learning, and it's really the heart of what makes all of this so incredibly powerful.